Let's start. So our today's speaker is Dr. Kerrek Stinson from the Institute of Applied Mathematics at the University of Bonn. So Kerrek got his PhD from the University from the Carnegie Mellon University in Pittsburgh. His advisors were Irene Fonseca and Giovanni Leoni. And Kerrek's research interests are interface evolution, phase separation, calculus of variations, and application in general. And today he is going to talk about regularity for minimizers of the Griffith fracture energy.
Perfect. Thank you. Thank you to the organizers for the invitation, and thanks to Barbara for inviting me to Prague. I'm very happy to be here. So, as was mentioned, I'm going to talk about regularity for minimizers of the Griffith fracture energy. This is joint work with Manuel Friedrich, who's at Erlangen and maybe here later today. I'm not sure who he's visiting. And then Camille Lamourie, who was a postdoc of his and is now at University Paris-Saclay. So let's see here. So I got to get the clicker to work. There we go. So maybe many of you know, maybe you don't. But so what we're looking at is a variational model for fracture, and this is the Griffith energy. And generally, when we're looking at elastic materials, there are a couple of things at play. For us, we're going to be looking at linearized elasticity. So we'll be just considering the displacement. And so here you take a reference configuration and you map it to a current configuration, and potentially you squish your object or you stretch your object. Then perhaps it's energetically a little favorable to actually break the material. And for this, we're going to introduce a crack or a collection of discontinuity points. And typically, I'll be denoting this. Yeah, the color is okay. It's the red. It's the red thing. There's a couple of pictures, and so typically, if you see red, it's a crack. Yeah. Okay. So these are sort of the two things that we're going to have at play: the displacement and a crack. And these will come together in the Griffith energy. In these two terms. So the Griffith energy is comprised of an elastic term, which just penalizes the stretching, so the sort of first picture. And the way we penalize the elasticity is through the symmetric gradient. And the important feature of the symmetric gradient is that it doesn't see sort of skewifying perturbations. And I'm sure all this is boring for everyone in this room. So the skewifying invariance is important because this is capturing framing difference, meaning if you or I look at the object, it's capturing the same energy. This is sort of the infinitesimal framing for that. The second piece that the Griffith energy also penalizes, which is maybe a bit more interesting, is it penalizes the length of the crack. So K is this one-dimensional discontinuity. And here we're penalizing the Hausdorff measure of this set. This is based on an idea of Griffith, which said that the amount of energy you release when you fracture material is proportional to the sort of size of the discontinuity or the size of the fracture. And this was sort of put out in the mathematical community by Frankfurt and Mario quite a while ago now. One of the other things to note about the model that we're interested in is it doesn't care, if you take a rock and you smash it on the ground and then you have your friend run off with half the rock, it doesn't matter how far away your friend runs, sort of the energy is the same. So the material is not cohesive. There's nothing gluing together the two sides. Once you've broken, it's broken. The other thing to note, which I'm maybe not going to emphasize too much throughout the talk, is everything I'm going to discuss is in dimension 2. So nothing I talk about applies to, okay, well, not nothing, but our results are limited to dimension 2, and it's for a very specific reason. Okay. So typically when you're looking at a variational model, you're interested in minimizing the energy. And minimizing the Griffith energy classically happens over pairs. So you consider basically a locally Sobolev function. So this is your displacement. You assume it's Sobolev away from the crack. And then the crack you assume is a closed set. That way you're sort of working with an actual Sobolev space on an open set. So you want to minimize over pairs like this. but it turns out the direct method doesn't do so great with respect to convergence of closed sets. And the way to deal with this is by relaxing your function space to a BG type space. So this was also done for Mumford-Shaw, and for elasticity, you have to relax to a BD type space, and this means bounded deformation. And it's precisely those functions, basically, which have this energy finite once you introduce the correct sort of twist of it. So to understand how to change the energy for the weak function space, you introduce an SPD type space, and this is all functions for which the symmetric or the distributional symmetric derivative, which is here in this calligraphic E on the left-hand side. So this is a measure, and the measure is decomposed into an absolutely continuous part, which is the little e of u times L2, or so the Lebesgue measure, plus a surface discontinuity, and that's the second piece there. So this surface discontinuity, which is arising in the measure, is really coming from points of discontinuity for your displacement. And so if you look at a function within SPD, you can then see that sort of the weak formulation of the Griffith energy is just replacing the discontinuity set by the jump set in the distributional formulation of the derivative. Okay, and then once you're here, you can actually apply the direct method to find a minimizer of the energy. And this was done very recently. So remember, the energy was introduced in '98, and in 2019, we have a minimizer to the Griffith problem. So this was done by Chambol and Crismal, and okay, published in 21. And then they built off this to show that actually, if you minimize over SPD type functions, the jump set is essentially closed. And so what that means is this collection of discontinuity points, if you take the closure of them and you subtract out the original discontinuity points, this JU, this is null with respect to the length measure. Now, why is this so convenient? Is what it tells you is actually the H1 measure of JU is the same thing as the H1 measure of the closure of JU. So now in this energy at the top, I could just say H1 of the closure of JU. And this means we actually have a strong minimizer. So you've started with this weak formulation and shown that you're actually back in the strong formulation. And I just want to briefly discuss why the strong formulation is stronger and why you can sort of think of it as a regularity result. So the way you prove that a weak sort of minimizer is essentially closed, or the jump set of a weak minimizer is essentially closed, is you prove a concentration estimate. And you show that if you take a point that belongs to the discontinuity set, so if I have X within JU, sort of discontinuity set, and I look at some small scale near that X, so a small scale denoted by R, basically in a ball around the point, there's a relatively large number of other discontinuity points, at least proportional to the diameter of that ball that you're looking at. And this is very nice because what it does is it prevents sort of unexpected behavior of the crack. So it prevents sort of having your crack diffusely spread to your region. So an example of something that can't happen now because you have a strong solution is you could expect maybe your jump set would look like you take any one of the rational points and you attach a little line to it. And then you just sort of attach a smaller and smaller line so that the H1 measure is finite. But in this case, let's see if I can, yeah, there we go. In this case, the H1 measure of the closure without the original jump set is actually infinite because of this. And so we can't have this happen, and really the crack actually should behave a little more like we would expect, like surfaces, and it concentrates. And so this picture on the right-hand side is more like what you expect when you have a strong minimizer. So, okay, this is sort of where we started. And what we wanted to do was understand finer properties of the regularity for this crack. And closed is nice, but it's a closed set, and that's not really much. We've been looking at closed sets for a long time. And And so what we did was we proved a slightly stronger regularity theorem for the cracks. And what this says is that there's a parameter delta, which is strictly greater than 0, such that for any minimizer of the Griffith energy, you can find a singular set of points contained in the crack, and this is denoted by the K star up here. And the dimension of this singular set of points is strictly less than the length measure. So this is the number of these points is sort of strictly less than the surface measure. Such that if you take any point belonging to the crack that's not one of these singular points, you can find some smaller radius such that the surface is actually a smooth surface. And so that's exactly what's happening in this picture. I've taken a generic point, or almost generic, and I can zoom in on some small scale, and it's a regular surface. Yeah, okay. And we get some other things, but maybe these aren't so important right now. Something we don't say much about is what happens at the points in K star. So these singular points. In principle, you could have triple junctions, you could have quadrillion junctions, you could have a lot of bad behaviors that we don't even approach. All we know is that there can't be too many of these bad points. Okay, so the way we prove this is through a couple of intermediate regularity results. The first one is an epsilon regularity result. And yeah, okay, I don't know how familiar you guys are. For me, epsilon regularity, or at least the phrase epsilon regularity, was new when I had to do this. And so all this says is that if you take, you have some locally defined quantities, and we'll specify these for this problem later. But these locally defined quantities, if they're beneath some threshold, then basically you can zoom in at whatever point these locally defined quantities are sort of centered around, and find out that you have some regularity property. And in particular, the surface is regular once these quantities are beneath the threshold. This is basically the bulk of our work. We also show that the crack is uniformly rectifiable, which is sounds slightly esoteric, but it turns out it's very helpful, and it gives you a control on how sort of broken up the crack is. And once you understand sort of some fine connectivity properties of the crack, you can actually use this to initialize the epsilon regularity result. We put these things together to prove a porosity result. And so this porosity result, you should think of it like, I mean, intuitively, something is porous if it has a bunch of holes, and if I tried to pour fluid through it, the fluid would actually get to the other side. And so when we talk about porosity, really what we're talking about is the porosity of the singular set, this K star. And so the porosity result says, take any point on the crack, you can jump close by to a neighbor, and this neighbor is actually a regular point. So then if you think in terms of the singular set, basically what this is saying is if you take any point in the singular set, you have a point that's close by that's a regular point. So if you had to flow through the domain and the singular points were obstacles, you would always have a neighbor that you could pass by. And it turns out once you have this porosity, you basically for free get an estimate on the dimension of the singular set. Okay, so I want to talk about the epsilon regularity statement. There were a couple previous results for epsilon regularity for minimizers of the Griffith energy. There was a paper by Babajan, Yerlano, and Lemonon, and this was just a two-dimensional result. More recently, so these are, I guess, publication dates. The first paper came out in 2019, and the second one in 2020. There was a paper by Laborie and Lemonon, and this was in arbitrary dimensions. Now, these are conditional, and they both rely on an assumption for the structure of the crack, which is that the crack is topologically separating. So they assume sort of an a priori assumption on the topological nature of the crack. And our goal is to figure out how you don't do that. So what is this topological separation condition? What you do is you take some ball in your domain and you zoom in and you look at this ball and you ask how the crack separates it, which in this case means if you have this region D plus on top and D minus on bottom, are they topologically connected? Can you take a line and connect them while staying in the ball? If they aren't, yeah, so if they're separated, it turns out this is very helpful because you can basically introduce variational competitors and get decay estimates. So a lot of times when you're looking at a minimizer and you want to try and obtain regularity of the surface, you need decay estimates for some associated quantities, and you will have to modify your minimizer on top and bottom. And so if I suppose, you know, this hand is the top side and this hand is the bottom side, and suppose I perturb my minimizer by pushing it this way and I pull back it on the bottom. If the crack is not totally separating, these two sides will see each other, and you'll have to pay for the elastic energy, sort of connecting the two sides. So once you're topologically separating, you don't have to worry about this. The other thing it's convenient for is that the different notions of flatness become equivalent, which I'll maybe explain what I mean by flatness in a sec, but this is more of a technical convenience. It's much more important that sort of it stops the two sides from talking to each other. Okay, and their epsilon regularity result was along the lines of the following. So what they said is that you have a minimizer and you have two quantities beneath epsilon, this is beta and omega, then and additionally the K separates. Well, then you can zoom in and the crack is regular. Now, what is this beta and omega? The beta is flatness, and this is basically asking how close is your crack to being a flat line. And then omega is your elastic energy. And so these are both sort of normalized in the sense that you divide by R. So the elastic energy, which is a surface, or sorry, a bulk integral. So normally you would think, maybe I want to divide this by R squared. But you only divide it by R because you're interested in the behavior of the surface. So you're looking at the scaling of the surface energy. Yeah, okay. And so maybe a bit of an idea for how you get sort of a regularity result like this and why the flatness is so important. So the flatness, if you look at a ball and you ask how close is it to being a straight line, that's what the flatness is measuring. It's asking how close are these two parallel hyperplanes that you can sandwich the surface between. And regularity boils down to basically showing a Holder type decay of the flatness. And the reason this is maybe not so surprising is that basically when you ask what line most closely approximates the crack in a small ball, you're finding an approximate tangent plane in some sense, approximate tangent plane, not the actual approximate tangent plane they use in geometric measure theory. And so when you get a decay of the flatness, you're basically saying that the oscillations in these approximate tangent planes are Holder. And then you can get that the surface is actually Holder. This is like Campanato's criteria that you use when you first do regularity theory for elliptic equations. So this is sort of where you want to go, and we'll maybe loop back to this. Our result looks similar in the sense that it's an if-then statement. So we show that if you have a minimizer and two quantities, the flatness and this J inverse are less than a threshold, then you can zoom in on a smaller scale and find out that the crack is regular. The most important thing here is we don't say anything about the topological separation. We don't need this. We have to introduce a new quantity to deal with the fact that we don't introduce or don't assume topological separation, and that is the jump. And the jump is going to capture the size of the discontinuity at this point. So here I haven't written this, but X belongs to the crack. So it has to apply at a point in the crack. And so the jump is capturing the discontinuity or the size of the discontinuity at that point on the crack. Okay, and then pictures, yeah. Now we know. I think we could have imagined, but if you're sufficiently flat, you can zoom in and you find out that on some smaller scale, you're a regular surface. So to understand how we prove this regularity result, it's perhaps a little more convenient to first think in terms of the Mumford-Shaw functional, which maybe some of you have seen before. So the Mumford-Shaw functional looks very similar, except it's for a scalar function. So U maps from R2 to R, not R2 to R2. And you penalize the full gradient. So for looking at regularity of the Mumford-Shaw functional, there's basically two approaches. One is a PDE-based approach, and there you consider sort of first variations of your energy, and this allows you to get a tilt estimate, which is like a reverse Poincare type inequality. The other thing you have access to when you're penalizing the full gradient is you have access to the core area formula. And the core area formula says that the integral of the gradient is the integral of the boundary of these level sets. Both of these things are unavailable for the Griffith fracture energy or the Griffith energy. Once you have vectorial and you're penalizing the symmetric gradient, you lose a lot of tools. So we need to sort of figure out how to overcome. Yeah, the lack of the core area formula is perhaps the biggest obstacle. Yeah, okay. So, but maybe to see how we can do this, it's worth asking how did they do it when they had access to the core area formula? And so what we're going to be interested in is we want to understand how far away the crack is from being topologically separating. Since we know how to do regularity theory, once the crack is separating, we want to understand how far away we are from being in that good case. And for the Mumford-Shaw functional, the way this is done is basically as follows. So if you zoom in on a ball that's at a jump point, and your crack is relatively flat, and suppose that in the top of the ball, your function is approximately equal to some constant b plus. And in the bottom of the ball, it's equal to some other constant b minus. Then to sort of find a way to sort of separate the top from bottom, you could consider the boundary of the super level set where you take the values of u that are greater than the average value between these two jump points. So basically this should contain all of d plus and then go much closer up to the crack. And so here in blue, I've drawn the sort of the line segment or the boundary of this super level set, which exists outside of the crack. So this is how much I had to extend the crack by to make it separating. And so if we want to introduce a measure for how much the crack fails to be topologically separating, we need to measure the length of this boundary. And if you have access to the core area formula, you can actually estimate the relative length of this boundary. So relative, yeah, okay, don't worry too much about these details, but you can measure the length of the boundary in terms of a quantity, which is the jump inverse, and then you multiply it by the elastic energy. And the jump inverse in this case is, well, okay, the jump itself is the difference in these two values. So you take the difference on top minus the difference on bottom, and you rescale by square root of r. And this weird rescaling is just coming from the fact that it's a bulk term interacting with a surface term. But the important thing here now is, so here this j, it basically looks like a constant divided by square root of r. So if you plug this in to the inequality above that, basically it's saying that the relative length of this boundary outside of the crack is going to 0 like square root of r. So it's actually vanishing. And it's vanishing at a Holder type rate. And this will be, is at least a priori, it seems helpful for the regularity theory. For us, we do a similar thing, which is we want to measure how far away the crack is from being separated. And for this, we introduce a new notion, which is the, I guess, relative length of holes or the normalized length of holes. Not a beautiful name, but we wrote it and we stuck with it. And what this is it's doing exactly what we did in the previous picture. It's saying you have a crack. How much do I have to add to the crack to make it topologically separating? And so here what we do is we consider the length of all possible extensions of the crack such that they separate, and we minimize over these extensions. So here in this picture, you have a crack in red, then the length of holes in this picture is just the length of the blue segments, which hopefully the blue are relatively clear. Yeah. So the good thing to note is maybe that if this length of holes is 0, then we're actually back to being topologically separated. So what we want to do is we want to figure out how to make the length of holes go to 0. To actually do this, we have to estimate this length by hand and construct extensions by hand. Somehow, a lot of times in these sort of regularity things, you can do things at the start qualitatively, and you can just use a sort of a compactness argument to find a contradiction, the same way you prove the Poincare inequality, when you at least do it by contradiction. It turns out it's not so clear how to use a contradiction argument to do this, so we have to actually use inequalities and estimates to estimate this length of holes eta. To do this, we introduce a new notion of jump. So in contrast to what we looked at for the Mumford-Shaw functional, and this new notion of jump is basically going to capture the difference in two affine or rigid motions associated to top and bottom. And these rigid motions are just coming from Corn's inequality. So previously in Mumford-Shaw, you were taking the difference of two constants, and this is what you would get if you were looking at the Poincare inequality. And so here, it's natural to take the difference in affine maps because you're interested in something that's invariant under these affine maps, and you can control them in terms of Corn's inequality. Yeah, in particular, it's these things, but I don't think we care. So with this notion of jump in place, what we want to do is prove something like a weak decay estimate. And this weak decay estimate says, as the jump blows up, the crack becomes almost separated. So the way to think of this is if I have an elastic material and I move one half over here and I move the other half over here, the crack actually wants to separate these two regions. Otherwise, you have to pay some stretchy part, which is going to have a lot of energy. So it's a very sort of weak estimate we need, or at least intuitively, it sounds very weak. And the reason we only need this is because of this following lemma. This lemma says if you take a point X on the crack and you look at all points near it, and at all points Y near it and all small scales S, you have that the length of holes is, let's see if I can find this pointer thing here. Nope, that's okay. If you have the length of holes at all these points in all small scales is beneath a threshold, then actually at the original point and on some smaller scale, the length of holes vanishes and you're actually topologically separated. And it's actually not so difficult to see why this is true. So if you had a crack and, okay, so now we have blue and black. Malte, can you tell the blue and black apart? Okay, good. Yeah, as long as, so the blue is just connecting, it's still acting as the extension. So in this picture, what I've done is I'm suppose that the top is connected to the bottom. And I want to see how far away this sort of, so now this gamma is my contradictory curve and it connects the top and bottom. And I want to estimate the distance from gamma to the crack. What I know is that since the sort of minimal extension of the crack that appears in the length of holes is separating, well then gamma has to pass through this extension because the extension separates it. And that means that the distance from gamma to the crack is at most the sort of length of the extension outside of the crack. The length of the extension outside of the crack is basically controlled by the radius of whatever ball you're looking at times the relative length of holes. And since I've assumed that the, there we go. since I've assumed that the sort of relative length of holes here, this eta, is controlled by 1/32, I get that this distance from gamma to the crack is controlled by r/32. And then I can just zoom in. So I find sort of the nearest point on the crack that's closest to gamma, and I zoom in to a new scale r/4. And on this new scale, I can apply the same argument to find out that the distance from gamma to k is controlled by the length of this extension in the smaller ball, but the length of this extension in the smaller ball is controlled by the new diameter times the relative length of holes. And the relative length of holes stayed bounded by 1/32. So now I find a smaller constant, and eventually just iterating this argument, you find out that gamma and k intersect. This seems like a basic idea, but somehow we really missed it, and we proved really strong decay estimates. And it turns out you didn't need them, because you could use sort of this clever topological trick to just show it vanishes at a certain point. The actual estimate we end up proving is here. And what this says is if you fix a constant kappa, and you can find a associated constant c kappa, such that for any minimizer and any point x on the crack, you can control the length of holes by this small constant kappa, and then you add a bad constant, which depends on kappa, times the inverse of the jump. And so we expect the jump to blow up, so this is okay, and basically this ends up giving us a control on the length of holes by eta. The way we prove this is a bit involved, and I'm not going to go into it too much today, unless you want me to, so then ask me after. And we use an analog of the Poirier formula. And this is something that Manuel proved, basically, I think in 2015, and then it was published a little bit after. And this is the piecewise Korn inequality. And what this says is if you have a function which has finite Griffith energy, then you can find a Kachopoly partition associated to your domain and associated skew-affine maps, AI, such that the difference of the sort of displacement and the affine maps is controlled by the original elastic energy, and the length of these partitions is controlled by the boundary of your domain and the amount of crack you had in there to start with. So if you haven't seen this before, it's maybe not so clear why this is an analog of the Poirier formula, but you can, starting from the Poirier formula, you can get a result like this for scalar functions, a stronger result. But yeah. So in pictures, it's exactly what we have down here. So we have our domain and we chunk it up into small bits, but not too many small bits because we have this perimeter bound. And on each one of these pieces, we have a Korn type inequality. Okay, so why is this helpful? What we can do is, let's see. Okay. What we can do in a first step is break up our domain into a bunch of pieces, and a large piece associated at the top and a large piece associated to the bottom, and a bunch of small pieces that interact finely with the crack. And then we can group them together to find a larger region here, which is given by this shaded in region. And this new object we can use to define an extension. So basically the appropriate extension here, E, is just given by the boundary of the set P united with the crack K. And so to actually get a control on the length of holes, what you need to do is you need to estimate the length of this boundary outside of the crack. Okay, and how do we construct this P and how we estimate the length of the boundary is by adding sort of, so yeah, here in this shaded blue region, I've added a bunch of the small partition elements. and you have to be careful which pieces you add, and you have to sort of track them using the Korn inequality, and then you can estimate the boundary length. And I'll leave that there for now. So once you have this sort of control on the topological separation, you're not actually quite done, and you don't end up immediately in sort of the topological separated case. You need to still do a bit more work. And for this, we still have to prove a couple decay estimates. And so you also have to show that the elastic energy decays. This is quite nice. The elastic energy at scale theta r is controlled linearly by theta times the original elastic energy. And then it's plus some error term. So it's m times the flatness plus the length of holes. And m I'll introduce in a sec. But this whole second piece, you should just think of this as some error term. We also get a decay for the flatness, which says that at smaller scales, somehow the flatness is being controlled by the other energies. And so the flatness squared decays like the elastic energy plus this same error term. Now, what is this error term? It's composed in part of the bad mass. And the bad mass is a sort of nebulous quantity that captures at what scale does your crack start having fine oscillations. And this is about as far as I'm going to go into it there. It's capturing sort of the way in which the crack set fails to be Reichenberg flat. We also need to show that the jump inverse goes to 0 or that the jump blows up. We can put these things all together to get a weak joint decay estimate. And what this says intuitively is small stays small at small scales. And this was sort of, this step is critical to sort of use the lemma that we discussed. So importantly, what it says is if you have a point X and on some scale R, you know that the length of holes are controlled by an epsilon. Well, then for all neighboring points and all smaller scales, actually you get the same control up to a sort of universal constancy. So now the length of holes is controlled by a small constant. And here you can just choose this epsilon 0 so that C times epsilon 0 is less than 1 over 32. 1 over 32 was just a random choice, but that's fine. Once you have this small stays small at small scales, you can apply the lemma to say that the length of holes actually vanishes. And also the bad mass vanishes, which we just take for granted. And then the decay estimates simplify a lot. In particular, the flatness squared is just controlled by the elastic energy, and the elastic energy is just controlled by itself times a linear factor. And plugging those things together, you just end up with a Holder type decay of the flatness. So beta decays like theta to the power 1/2. And so this is when we get that it's a C1 1/2 surface. Okay, so I'm going to briefly discuss uniform rectifiability and maybe try to explain why it's helpful and not quite so esoteric. Rectifiability for a set basically just says that you have a atlas composed of Lifshitz maps. So you can cover the set by just a bunch of Lifshitz maps. Uniform rectifiability says there is a single map which you can use to cover the set, and this map is basically by Lifshitz. So it's Alfor's. And the reason, it's now uniform is your set K will inherit properties from the sort of single Lifshitz map, which has a single Lifshitz constant, and this will be nice. So we actually prove something slightly weaker, which is locally uniform rectifiability, but it's potato. The way we do this is we use an equivalent characterization, which maybe brings out the reason why I think of this as a form of connectiveness. So what we show is that if you have a minimizer, and you take some point X within the crack and some ball centered at that crack, you can find a compact and connected. So importantly, it's connected. So this connected set gamma, such that gamma has a large intersection with the crack relative to the diameter of the ball, and the length of gamma is controlled by the diameter of the ball. And so in a picture, it's what's happening down here. So I have my crack, K. I can find a curve, gamma, which basically passes through the ball and intersects the crack for a relatively large region. That's its first inequality over here. And the second one is saying I didn't have to squiggle a bunch in the ball to actually cover the crack a bit. So we actually prove this using related techniques to sort of similar techniques that we use to get the estimate on the length of holes. Once you have this, and the reason why we actually prove uniform rectifiability, although it might be a nice property, is that it allows you to initialize flatness. So once you know that you're uniformly rectifiable, if you take any point on the crack, you can find a neighboring point. So if I've taken any point X on the crack, I can find some neighboring point, which is at most, the original scale that you were looking at far away, such that the flatness on this, at this new point and some smaller scale, is less than epsilon. And this is important for us because we need flatness to be small to kick in our epsilon regularity result. And why we want to kick in the epsilon regularity result is to get control on the size of the singular set. So the singular set is basically, it's all points such that there's no small scale on which the surface is regular. And intuitively, this is basically just all points where the epsilon regularity statement doesn't hold. And yeah, so what we do is we show that the epsilon regularity statement can kick in at most points, or a lot of points, or near most points. And this is the porosity. And once we have the porosity, we get a dimension estimate on the crack, or on the singular points within the crack. So as maybe been hinted at before, what we show is that if you have a minimizer and you take a point on the crack, you can find a neighboring point such that the crack in this in a small ball centered at the neighboring point is a smooth curve. As I said, uniform rectifiability is used to initialize flatness. We also have to initialize the jump. And this is not a problem for Mumford-Shaw at all. And it turns out because you have these affine maps, which are sort of, you're basically freely rotating one side of the rock and the other one is staying fixed, or vice versa. And you have to sort of fix a frame of reference to make sure that you can show that the jump is sufficiently large. So we also do that here. Yeah, okay. And so with that, there's quite a few nice questions that are sort of still out there. Something that we're just now putting together and hopefully will be done soon is we're showing that the cracks are closed for a sort of large class of Griffith type energies, so including anisotropic energies, partially cohesive energies, but not sort of degenerate cohesive. There's also the question of what the crack looks like near singular points. So we didn't touch this at all. We just said there's not too many singular points, but if you go off what happens in the Mumford-Shaw setting, what you expect is triple junctions and crack tips, and you expect nothing else to be okay. The other thing is higher dimensions. So the reason our result is only valid in 2D is because Manuel's piecewise Korn inequality only exists in 2D. And once you sort of unlock the appropriate version of this in higher dimensions, everything else we have, it's the right framework and things should go through. That's the limitation. And with that, I thank you.